verifier for combinatorial conjectures.
All right, so thank you. So I'll be talking about MathCheck2, which is a system that I helped develop. And so the major sort of theme of the talk is going to be sort of linking these two areas, SAT and CAS, SAT being satisfiability checking and CAS being computer algebra systems. So this is a quote from Erica Abraham, but an invited talk at Isaac last year, which is one of the main symbolic computation conferences. And so she pointed out we have these two communities in computer science, which are kind of separated. We have, on one hand, the SAT solving community, and on the other hand, we have the computer algebraists. And they both sort of, the communities have their own strengths and weaknesses. The SAT community is typically put a lot of effort into making general purpose search tools called SAT solvers, which basically you give them a logical expression, and it can spit out a solution or no solution exists, right? And so it's kind of does it, you know, quasi brute force. There's a lot of sophisticated heuristics to go into these things, and also a lot of learning. So as the SAT solver is doing its search, it's keeping a database of facts that it's learned and adding to that database, and then using those facts that it learns as it's going to speed up the search in the future. All right, so this is kind of advantages that aren't really present in typically in computer algebra systems. So computer algebra systems are more, there's lots of sophisticated algorithms in mathematics, but they're kind of domain specific. They don't typically have these general purpose search procedures. So what we're going to try to do is, you know, use the best of both worlds to develop a tool which sort of bridges these two areas. All right, so the SAT problem I think everyone has heard of. This is, you know, the classic problem in computer science. Given a logical formula, determine if it's satisfiable. So an example here is the formula on the bottom of the slide here. The variables are booleans, either true or false, and then the things connecting them are logical operators, so and or not. All right, and so you feed this into a SAT solver and ask, is this formula satisfiable? Are there some assignment to these variables which makes the whole formula true? In this case, if you feed that into a SAT solver, it'll say, spit out, yes, this formula is satisfiable, and then it'll spit out an actual satisfying assumption, or satisfying assignment. Or if it's not satisfiable, it'll say, no, this is unsat, and then sometimes you can also, some of them will output a reason why it was unsat. All right, so like I said, we have two sophisticated tools, computer algebra systems, such as Maple, Mathematica, Sage, and then there's lots of sophisticated SAT solvers, which people are continually improving, making them more and more efficient. Right, so people compete on these things. But there's not really any standard protocols for talking from one system to another. So we wrote some scripts which basically can talk to both, right? And so the demo that I'm going to be talking about in this, and which we've kind of worked on so far, is that from combinatorial design theory, we talked about, we're looking for Hadamard matrices and Williamson matrices, which I will define in more detail. But at a high level, this is what's going on. We're going to be looking for a specific instance of a Hadamard or Williamson matrix. So we take as input the problem, and then the generator is going to translate that class into a format that the SAT solver can understand, and we'll typically split up the search into multiple subspaces, throw those instances off at a SAT solver, get results back, and then either if it's a SAT result, we're going to produce a solution. If it's unsat, we'll try to see why it was unsat, and then use that to make the prune away other instances. And then in the meantime, we'll be querying the CAS to try to learn facts about, you know, from mathematical theorems, right, that the SAT solver probably doesn't have access to. Right, and then again, pass those off, add them into the SAT database that it's using to make its search proceed. All right, so continuing with the theme of going over the conclusions before the talk, this is the sort of the advertising of what we've done so far. So I'll define these things as we go, but Williamson matrices were used to construct Hadamard matrices. as it was shown by the mathematician Djokovic that they don't exist in order 35. And so he used a computer program to do this. And so, he proved some theorems and then implemented them and got the result. But there's always that nagging feeling in the back of your mind, right? When you have a result like that, what if the program has a bug, right? Because there's no nice short certificate of this result. So this is why you kind of want an independent verification, right? You want a separate team with a separate algorithm on separate hardware to do the same result, and then you have a little bit more confidence that there wasn't a bug in the first place. So we did that. So our system, when it was all said and done, the system ran in about 9 hours on this computing cluster SharkNet. We were also able to show that for all smaller orders, Williamson matrices do exist and produce them. As it turned out, when n is even, there wasn't much or any literature on this. All the previous algorithms had actually assumed n was odd because there's some special structure that those algorithms took, used in their running. So there was some new ground that we were covering. And then, so people care about Hadamard matrices. They, collect libraries of these things. There's one in the computer algebra system, Magma. Sloan has an online library of Hadamard matrices. And so what people care about are finding new Hadamard matrices which aren't equivalent to previous Hadamard matrices. And so we were able to contribute some. All right, so now getting into the details of what's going on here. So if you hadn't heard of Hadamard matrices, they're objects from combinatorics, which are deceptively simple to define. So they're matrices which are square. They have plus minus 1 entries, and the main criterion is that any two distinct rows are orthogonal. So their inner product is 0. So extremely simple to define. You can kind of work out one in your head. If you're given something like this, you can check out all pairs of rows and see, take their inner product and see, okay, the ones and negative ones cancel off, and all the inner products are 0. All right, so this is the 4x4 Hadamard, and the conjecture is that for any n multiple of 4, an n by n Hadamard exists. So this is sort of the big open problem in this area, and so it's known that this is a necessary condition for any n larger than 2. If a Hadamard exists, then n must be divisible by 4. Whether it's sufficient or not is the big open question. It's widely suspected to be true, however. So people look for these things, and so we wanted to try to attack this problem. One of the reasons why we, this problem was attractive to us was because of the kind of Boolean nature, right? So we're going to be translating this into a format that the SAT solver can understand, and because we have plus minus 1s, that's a very nice. You can translate that into a Boolean setting easily, right? 1 will represent by true, negative 1 by false. Furthermore, the multiplication also can be translated quite nicely, because if you write out the truth table of these things, negative 1s multiplied together is also negative 1, or plus minus 1. So you write the table, you get basically just an XNOR function. Right? So SAT solvers can compute this no problem. The addition is a bit more cumbersome. So this is the actual, the formula. At the top here is the actual inner product that we want to be 0 for a matrix to be Hadamard. So we can compute the inner sum end. There is just a multiplication, so we can compute that. We're going to introduce new variables. We'll call them product variables, Pijk. And so then what is this sum being 0 saying? Well, we have n terms in the sum, and if they're to go to 0, that means exactly half of them are going to be 1 and exactly half are going to be negative 1, right? Because they have to cancel off. So what's that saying? We're saying that half of the Pijks are true and half of them are false, right? So if you write this as a cardinality constraint, at the bottom here you're saying n over 2 of the Pijs are true. And so this is what we're going to encode in SAT. And so, well, how do you encode a sum of 1s in SAT? Well, 1 plus 1 is 2. How do you encode 2 in the Boolean setting? We're going to use binary numbers, right? So a binary adder here, we'll think of the inputs now as bits, and this is a 2-bit binary adder. If you, the outputs are going to count in binary how many inputs were set to true. All right, so this is just 2 bits, so you can use a network of these things to make an n-bit binary adder. And so what we're going to have, we'd have n inputs representing the PIJKs, and about log n outputs representing how many of the inputs were set to true. Right? And we're going to want them to be exactly n over 2 inputs to be true for the thing to be Hadamard. All right, so this is how we do the encoding. All right, so we implemented that, we fired it off, and then the problem is you're up against an exponential, or worse than exponential search space, because you have about n squared entries, each one can be plus minus 1, you have like 2n squared. That's the sort of naive search space, right? So you hit a wall pretty quickly, but people come up with cleverer ways of constructing larger and larger Hadamard matrices. And so this was one way that we considered to use Williamson matrices, so Williamson matrices are not themselves Hadamard, but they have a close relationship. You can construct Hadamards from Williamsons. All right, so here's the definition. It's not too bad. You have 4 matrices, which are square n by n, entries plus minus 1. They're symmetric and circulant. I'll come back to that. And the last condition is the non-trivial one. The first 3 are pretty easy. The last one is basically a sum of squared matrices is equal to the identity. This is basically a quadratic Diophantine equation that you want to solve. So it's not completely clear how I can go about that. So symmetric and circulant, if you're not clear on these terms, I think everyone knows symmetric, right? You can mirror the entries across the diagonal. Circulant is basically saying the first row defines the entire matrix. You can take the first row, shift it down and to the right by 1 to get the second row, shift the second row down to the right by 1 to get the third row, and then you can fill the whole matrix that way. So if you have a symmetric circulant matrix, what you'll see is that basically the half of the first row defines the whole matrix. So really, we're just actually not searching for matrices, we're searching for sequences. So if we rewrite the Williamson conditions as in terms of sequences, this is what you get. The sums of squares condition becomes a sum of what we'll call path values. So this is just for convenience. We're going to define this path function at the bottom here. It's what you get if you use naively translate those matrix multiplications into sequences. And actually, path is convenient in other contexts as well. Many combinatorial objects can actually be defined using the path function. Anyways, the only thing we really need to know is that this is pretty easy for a SAT to compute. SAT's already can compute this, right? Just using the exact same binary adder encoding that we already did. It's just addition and multiplication. All right, so one last piece of background before we get into the results. Okay, so compression. Again, we want to search for as small objects as possible because the search space is just so enormous. So anything that we can do to compress the objects is going to be beneficial. The downside is we're losing some information when we do the compression, but it's going to be in a very structured fashion. There's going to be a lot of invariants that will translate over to the compressed sequences. All right, so definition of the compression is on the top. We probably want to look at the bottom where you see an example of how these things work. Let's say we have a 10-element sequence here. We're going to compress it by a factor of 5. Then what we're going to end up with is a 2-element sequence whose first element is the sum of the red entries, which is entries of even index in the original sequence. And the second entry in the compression is going to be the sum of the entries of odd index. But since 10 is also divisible by 2, we can compress by a factor of 2, and this is what you get. All right, the first entry is now the sum of the 0th and the 5th term, and so on. All right, so compression is easy to define. Some nice properties. You can get some very nice bounds on the values of the compression. It turns out the parity has to be the same as the parity of M, where you're doing M compression. And the compression of a symmetric sequence is also symmetric. So symmetric sequence can be reflected around the midpoint. All right, so those are some nice lemmas. The main theorem that we used was of Jakovich and Kotsireas. This is a special case of it. Williamson sequences are going to satisfy this sum of paths. So you take the paths at 0, add them up, you're going to get 4n. Right? And it also holds for any compression of the sequence. So in particular, let's just look at the easiest thing you could possibly do would be to maximally compress the sequence. If you maximally compress it, you shrink it down to a single element, well, that's just adding up all the terms of the sequence, right? So when D is 1, we're compressing it all down to a single element, and we'll just call that the row sum, right? You're adding up all the terms in the sequence. And then a path at 0 is just a squared function. So this just reduces to a sum of squares. And that's going to be sum of squared row sums. That's going to sum it to 4n. All right. So why do we go and do this? What is this useful for? All right. So this is where the CAS comes in, because the SAT solver, as it's doing its search for these things, is probably not going to be able to derive this theorem on the fly, right? I mean, we've proven it. We know it's true. In theory, if the SAT solver was smart enough, they would be able to find this out by itself. But it's unlikely, because this is the downside of doing all this translation into logic, right? We've lost the context. The SAT solver doesn't know where the variables that we gave it came from, right? It just knows true or false. So it's lost the context of the problem. So what we're going to do is use the CAS to feed in some information to the SAT solver. Just stick it into the SAT solver database as it's running. All right, so anyways, a CAS function, like in Maple, or if you go to Wolfram Alpha, you can have it solve this for you. There's not normally too many possibilities when n is moderate size. And so anyways, we have explicit values of all possibilities for w, x, y, z. So we're just going to feed in the bottom 4 constraints into the SAT solver as it's running. We're going to say, okay, the row sum of A must be w. And there might be a couple of instances of w, but that's fine. And we can compute row sum in the SAT solver, no problem, right? Just use a binary adder again. All right, so an explicit example here, we have exactly 3 ways to write 35 as a sum of 4 squares. And they're explicitly given here. Which is not technically true, because you can always, there's a bunch of symmetries there, right? You can permute the entries, you can negate the entries. Actually, that's irrelevant, because you can do the same thing with the Williamson sequences. And then you just get another Williamson sequence, which is basically isomorphic. So, we'll just kind of discount those, sweep them under the rug, because they're just basically spurious solutions that enlarge the search space unnecessarily. So we can also enforce this. So we have basically 3 possible sums of squares decompositions for the 35 case. All right, so that was the first technique that we're feed some extra information to the SAT solver. Second technique is to split up the instances into parallel ones. So 2 reasons. One is parallelization. We have large clusters of many cores, and we fire off a SAT solver instance in each of them. The second is because it's another place where we can use the CAS power. Right? The CAS will be able to do a splitting in a nicer way than the SAT solver itself, because again, SAT solvers, some of them are parallel, but again, we can probably do a nicer splitting than the SAT solver can. So we tried a couple of different ways of doing splitting. In our case, actually splitting by compressions turned out to be pretty effective. So basically, each instance is going to have a separate compression. So we're going to derive all possible compressions for looking for a certain Williamson, and then you're going to fire each SAT instance is going to only be looking for one specific compression, right? And it's going to try to uncompress it. See, does this compression lead to an actual solution? And the main theorem, so you can try to generate all possible compressions. We use lemmas 1 and 2 to sort of get a baseline. That's still kind of way too many possible compressions. So we're going to use this theorem, the decay theorem I mentioned, which is also has some statements in terms of power spectral density, which this is kind of again, this is something from, a computer algebra system can compute a Fourier transform. The power spectral density is just the squared norm of that. So we can compute this no problem in a CAS. And what really you don't really have to know, what a Fourier transform is to understand this. You just need to know that the power spectral densities are going to be non-negative numbers. All right, they're all because we're squaring a real number. All right, so given that they're non-negative, let's look at what the theorem says. So the theorem says Williamson sequence satisfies the sum of the PSDs is always going to be 4n. So this is kind of surprising. And even furthermore, even if you replace these sequences with their compressions, this still is invariant, it still holds. So right away, we have a nice corollary that the PSD of any Williamson sequence or any compression of a Williamson sequence is always going to be at most 4n. Right? Because if it was ever larger than 4n, you're never going to be able to satisfy that equation at the top because everything, all the other three terms are not negative. Right? So anything, so this is where we can really filter out many, many sequences because most of the sequences, when you just try them, are going to have a PSD larger than 4n. All right? Because you can try like lots of values of s, and it's likely that one of them will have a PSD larger than 4n. All right? And so we just put that possible compression in the trash because it's never going to uncompress to something that we want. All right, so this is just an explicit example. So out of millions of possible compressions, we have used that theorem to limit it down to just 119 possible 7 compressions of a Williamson of order 35. All right, and that one of them is given here, right? Just so you can get a feel for what these things look like. Actually, in practice, we found it was even a little faster that we actually did compression both by 7 and 5, because 35 is divisible by both of those primes. And it makes it a bit more complicated. It greatly increases the number of instances because you have to try all possible 5 compressions with all possible 7 compressions. Right? So you have to try all pairs. So in the end, it was about 22,000 instances of these 3 types. But the fact that each instance had a 5 compression and a 7 compression was very restrictive. Right? The instances ran really quickly. So this is what we ended up doing. Last technique was what we call the UNSAT core, which basically was, like I was saying, when you get an UNSAT result from a SAT solver, sometimes you can configure it to say, also output why the result was UNSAT. It can say, this was UNSAT because I set this variable to this variable to this variable to this, and I was able to derive a conflict. This was UNSAT. So because of our instances are so similar looking, we have lots of instances, but they're very similar, this was often able to, when we got that result, we were able to prune away other instances, right? Because most of the work in the logic instances were doing the binary adders, which were identical throughout. The equations were identical. The only thing which were different was the specific values of those compressions. Those differed from instance to instance. So, anyways, that was the last technique, and I'll show you the experimental results. So, basically, the first technique only got us up to 30, and then you hit a wall. The first technique got us up to 31, and then it was divide and conquer, which allowed us to actually prove the non-existence in 35. UNSAT core was a bit of hit and miss. Didn't decrease the time all that much in some of the cases. Sometimes it about halved it. It was curious that it was able to greatly decrease the number of SAT calls in certain cases. So basically, there was some structure in those instances that basically our theorems didn't, we hadn't implemented them in the theorem. So maybe there is a theorem out there that would be able to have done that for us, but it was able to automatically sort of tell us, okay, all these instances were UNSAT because of this, because of these variables were set to this. So it was kind of nice that it automatically knows that. All right, so the main thing, the reason why I was talking was because I wanted to, try to bridge these things. Actually, there's going to be some workshops later in the year, which kind of exactly on this topic of you search for SC square. SC squared being symbolic computation and satisfiability checking happen to have the same initials, right? So SC squared is sort of the buzzword. And so yeah, so it's sort of a prototype system at the moment, but the 2 main results I wanted to highlight was the non-existence in the 35 case, and then the existence in everything less than 35. Anyways, I'll take questions, and thanks for the time.